acephysics.org. I'm going to go over an example problem. This problem is the boat crossing a river vector example problem. The river has current. This is a common physics problem describing a boat crossing a river with current. It utilizes many important vector concepts such as visualizing velocity vectors, adding vectors, converting vectors between component form and angle magnitude form. It's a multi-part problem. To begin with, I'm going to read the problem. A boat which has a speed of 9.6 meters per second in still water heads directly across a river. The river has a current of 3.8 meters per second and is 1,860 meters wide. Part 1. How long will it take the boat to reach the opposite side of the river? For any physics problem, you first want to sketch a little diagram of what's going on. This is the river. This is one shore of the river. Here's the opposite shore of the river. The river has a width of 1,860 meters. The boat's maximum speed that the engine can make the boat go in the water is 9.6 meters per second. And then there's a current going to the right. If the bow of the boat is headed directly across the river, then the boat's velocity will point off at some direction. And this is because velocity is a vector. The velocity of the boat is a vector. In order to get the velocity of the boat, you need to add up the velocity of the boat relative to the water plus the velocity of the current. And this black arrow right here is the velocity of the boat relative to the shore. The velocity of the boat equals 3.8 I hat plus 9.6 j hat. It has both an x and a y component. The question asks for how long will it take for the boat to reach the opposite side of the river. A standard equation in physics is velocity times time equals distance. Here we have to use the velocity in the y direction times time equals the y distance. So the velocity in the y direction is 9.6 times time equals 1860, or time is equal to 193.7 seconds. The reason we only use the velocity in the y direction, which is 9.6 meters per second, is because the entire point of vectors is that the x component and the y component are decoupled. Whatever happens in the x direction has no effect on the velocity in the y direction. If the current suddenly sped up to 1,000 meters per second, it would still take 193.7 seconds for the boat to cross the shore. To cross the river, the boat would just end up farther downshore if the current was quicker. Question 2. What will be the velocity of the boat as measured by an observer standing along the shore? Write the velocity in component form as well as give the magnitude and direction. In part 1, we already wrote the velocity in component form, and this is the velocity of the boat as measured by an observer on the shore. Now we want to convert it from component form to angle magnitude form. And in order to find the magnitude of the vector, you take the square root of each one of the components squared, and that's 10.3 meters per second squared. That means that the length of this velocity vector is 10.3. In order to get the direction, you must find the angle theta. Tangent of theta is equal to opposite over adjacent. Opposite is 3.8. Adjacent to the angle theta is 9.6. You can then take the inverse tangent of both sides and get this angle. Therefore, the vector in component form is 3.8 I hat plus 9.6 j hat. The velocity vector in angle magnitude form is it's a velocity of magnitude 10.3 meters per second, and it has an angle of 21.6 degrees east of north. You start north and you move 21.6 degrees east. Part 3. What will be the final displacement of the boat when it reaches the opposite shore of the river? Write the displacement in component form as well as give its magnitude and direction. So this part of the problem wants us to find the displacement vector starting from this point and ending at this point. If the bow of the boat is headed directly towards B, the boat will end up at some location downshore here, and the displacement vector has both a y component as well as an x component. We know the y component is 1,860 meters because that's the distance, that's the width of the river. What we need to find is how far downshore the boat goes, and that's the x component. Again, I'm going to use the formula velocity times time equals distance. Now I'm going to use the velocity in the x direction because that's what matters in order to find how far down the shore the boat goes. Velocity in the x direction times time is equal to the distance in the x direction. The velocity in the x direction is 3.8 meters per second. We got the time from part 1, and therefore the distance in the x direction is 736.1 meters. The displacement vector in component form is 736.1 I hat plus 1,860 j hat. If you want to convert this to angle magnitude form, which the question asked you to do, so you do want to do that. You find the magnitude of the displacement vector d, which is the square root of the component squared, and that's 2000.4 meters. And then the angle is 21.6 degrees east of north. And I know that the angle is the same angle as the velocity vector, but it might be good practice for you to use the displacement vector and check using tangent of theta that you get the same value. Problem 4. What should the heading, direction of the boat, of the boat be if it is to land at point B directly across the river? So now, if the boat is to land directly at point B, which way should it head? If you point the bow of the bow directly towards B, it won't land at location B because the current will push it and will land here. So the bow of the boat has to be pointed against the current such that the velocity of the boat in the x direction cancels with the current and the boat only has a y component of velocity. So the boat has a maximum speed of 9.6 meters per second. It's going to be going at some angle theta, and I know that the x component of the boat must be 3.8 meters per second because the current is 3.8 meters per second going to the east, so the velocity of the boat must be 3.8 meters per second going west, such that these two velocities cancel each other and the boat only moves in the y direction, only has a y velocity. Therefore, this triangle leads to the solution of this problem. You have two sides, and when you have two sides, you can solve for everything else. So we know that sine of theta is equal to opposite over hypotenuse. Therefore, sine of theta is 3.8 over 9.6, and theta is 23.3 degrees. And you must put in, I left off one thing, and so it's 23.3 degrees west of north. So here's an example to help visualize this. There's a gentleman here who's swimming, basically on a treadmill. The current is going backwards. He's swimming forward, and he's not moving because the current and his velocity are canceling each other out, just like in that problem. The velocity of the boat and the current cancel each other out. And it works with the breaststroke. It doesn't matter what stroke you do. If you are swimming at the same speed as the current, you will just stay in the same location. And finally, part 5 says, assume the boat has a heading from item 4. How long will it take the boat to reach the opposite shore of the river? So this is the velocity from the previous part 4. We know that this is 9.6 meters per second. The velocity in the x direction is 3.8 meters per second. The angle is 23.3 degrees. This is the velocity in the y direction. We don't know it. We need to solve for it. Cosine of theta is cosine of theta is adjacent over hypotenuse. Cosine of 23.3 is adjacent, which is Vy over 9.6. We can then multiply both sides of the equation by 9.6, and this says that Vy is 9.6 cosine of 23.3, or Vy is 8.8 meters per second. And the question is, how long will it take for the boat to reach the opposite shore? We use velocity times time equals distance. In this case, the velocity in the y direction is 8.8 times time is equal to the width of the river, 1860, and it takes 211.4 seconds for the boat to get to point B if its heading is that way and if it wants to go directly across the river to point B. It actually takes longer to get directly to point B than it would to get to this location.